Okay, hello Math 352, welcome back. So we're up to lecture 7, and today we're going to pull together some of the material we've done in the last couple of lectures on QR factorization and on projections, and apply them to a really useful topic, which is that of least squares. Okay, so without any further ado, let's just get straight underway. Okay, so far, when we've thought about solving equations, we've been looking at equations that look a bit like this. Okay, so we've got equations ax equals b. Typically we'd have a square matrix A, we'd have a vector x, and we'd have a vector y. Okay, now that's often completely natural thing to be trying to do. Solve an equation with, I don't know, m unknowns and m equations, and you can solve for the m variables x just by solving a linear system by Gaussian elimination or something. Okay, but let's say, for example, that we have a system now that has more equations. So let's say that A now looks like this. Our x is still going to be the same size, and our B is also going to be the same size, as the same length as the matrix A. Okay, now that equation has more equations than unknowns. Okay, and unless you get really lucky, there actually won't be a solution x to those equations. Be a solution. Okay, so if we've got such a system, it's called an overdetermined system. Okay, overdetermined. There are too many equations. Okay, so we almost overdetermine our solution. Okay, so instead of finding an x that matches, instead of finding an x to solve the equation, we find an x that minimizes something. Okay, so you're going to try and find the best x in some sense for that system of equations. So the least squares solution is the one that minimizes the 2 norm of what we call the residual. Okay, where r equals ax minus b is the residual. Okay, that's kind of a natural thing to try and make small, because if the system could be solved exactly, then ax minus b would be equal to 0. If it can't be solved exactly, then you're trying to get ax minus b as small as you can. Okay, so the square of that. So this is called the least squares, or the linear least squares problem or solution. Okay, so that's one of the types of systems we're going to be looking at today. Now the other one is when we've got the opposite problem. Okay, let's say instead of having too many equations, we don't have enough. Okay, so now we've got an A that looks like this. Our x is going to be like that. And our b will be small. Okay, this one has fewer equations than unknowns. And there will typically be infinite solutions. Okay, so what do we want to do in this case? Well, given that we can solve it and there are infinitely many solutions, what you're often interested in doing Okay, obviously you're not particularly interested in just finding a solution, because that's quite easy. What you're interested in doing, we want to find the shortest, okay, or the lowest norm x that solves it. The shortest x solving ax equals b. Okay, this is known as the least norm solution. Okay, and we say the system is underdetermined. Okay, so the one we had before was overdetermined. This one is underdetermined. There aren't enough equations to uniquely specify x. Okay, so we're going to look at these two problems today. The first one we're going to look at is the overdetermined case, and that's much more common. Typically when you're solving a scientific problem, you'll often end up solving an overdetermined system, and we'll have a look at why. Actually, we'll start there. So, overdetermined systems. Okay, so let's say we've got some kind of physical system. Let's just say it's a black box for now. Okay, and what we're going to do is system takes in an input, for example time, and it gives an output. We'll call it ti, which we'll call yi. Okay, so one way to think about this is we could sample our system at different times. Okay, we could just choose different times, and for each time it gives you an output y. Okay, and let's say we have some idea that what the system is doing is something like this. Y equals x1 plus x2 sine t plus x3 cosine t. Okay, because we know something about the physics or the setup of our problem due to its context. So we have some kind of guess that what it's actually doing is some kind of sinusoid like this. Okay, and from the context of the problem. What we want to do, therefore, is work out what x1, x2 and x3 are. x3. Okay, and we'll just say we have m samples. Okay, so I've stuck in m different t values. I equals 1 to m. Okay, so what we want to do is we want to use our samples to work out what x1, x2 and x3 are. Okay, we should just say one more thing. The samples are noisy. Okay, so when we measure our y, it doesn't exactly fit the equation. It's just going to be close. Now that could be due to our model only being approximate, or it could be due to the accuracy of our measurement instruments, or a combination of the two things. Okay, so let's flick over to MATLAB, and I'll show you some samples that our system produced, and just so we can get a bit of a feel for what it looks like. So I've loaded them into a file, so let's just load that file up. Load lsq samples.mat. I'll stick this on Learn afterwards so you can have a play with it. Okay, so let's have a look at them. So we'll plot the samples. So you'll notice that when I loaded that mat file, I could have just double clicked on it here as well and loaded it from there. I got these variables ts and ys appearing up in my workspace. Okay, so let's plot them, and I'll plot them as blue circles, just so we can get an idea of what it looks like. Okay, so here's our samples. So you can see that, if you imagine, I'll use a little bit of imagination, it does look kind of like a sinusoid. Okay, let's make those markers a bit bigger. Okay, probably too big, but oh well, not to worry. Okay, so here are my samples. We can see they sort of look like a sinusoid, and what we're effectively trying to do is fit this sinusoidal relationship to them. Okay, so let's go back to the theory and see how we can do that. So we can set this up as a matrix equation. Now, your first instinct might be that this isn't a linear system. It's got sines and cosines in it, so how could it be linear? How could we describe it as a matrix? The key thing to realize is that the system is actually linear in x. Okay, it's linear in the thing that we want to find. So we can write as a matrix equation. Okay, so what will our equation look like? Well, it will look like the first row should say, well, let's just start setting it up. We know that our unknowns are x1 through to x3. We should have 3 entries going across our A matrix, and we'll have some right-hand sides. Okay, so for the first data point, for I equals 1, we have that yi, or y1, is equal to x1, so it's one of those, and it's going to be sine t x2s, so we stick sine t1 here, and it's going to be cos t times x3, so it'll be cos t1. So my first sample can be put into the equation like this. Except, like I said, it's not actually an equation, so we won't write equals there. We'll write approximately equals, or something like that. Okay, so we can stick in the rest of our samples like this. Cos t2, y2, all the way down to the last one, which will be tm. And ym. Okay, so we've got ax here, and we're hoping that we can find x so that ax is somewhat or approximately equal to b. Okay, so let's zip across to MATLAB and do that bit as well. So how can we can actually construct this quite nicely. I'll show you how to do that. So we'll get rid of that picture for now. So first we need to know what m is, how many data points we've got. So m is just the number of elements in t or y. N equals 3, well I don't really need that. A, we can just stick this together piece by piece. The first column is just 1. Okay, if you just look back at here, the first column is just 1. So I just want a vector of 1s that has m rows and 1 column. The second column is sine of each of the t's. So I can actually do that in one hit. Sine ts. Now I have to make sure that ts is a column vector. Okay, if you look at what it is, ts is currently a row, so sine ts is not going to give me a column of t values. A nice way of forcing a vector to be a column is to just go like that. So that's just a little one of these little tricks that you can have up your sleeve. If you want to force a vector to be a column vector, whether it's a row vector or a column vector, then doing that bracket colon bracket will do that for you. The last column is just cosine of each of the entries. Once again, we'll just do the same thing there. So that should give us our A matrix. Okay, and our right-hand side B was given by the y values. So we'll just set that to be y, and we'll make sure it's a column as well. Okay, so if I run that again, I don't really need my picture right now, so I'll just comment that out. you can see that my A is a matrix of the right kind of shape, and my B is a vector. Okay, so what we're trying to do is find an x that makes AX be approximately equal to B. And there won't be one that works exactly, I'll tell you that right now. Okay, so how do we do that? So we've set up the problem, we haven't yet set up how to solve it. So there are two main ways of doing this. The first one is not as good, but it may be the one you've come across before, and it's also the fastest. It's called the solution by normal equations. Okay, so we're trying to minimize AX minus B. Okay, so let's have a think about that for a second. We've got B, which is a fixed vector. We're trying to minimize the difference between B and the matrix A times X. Now if we think back to what we've been doing a little earlier, AX is a vector in the column space of A. It's just a linear combination of the columns of A. So we're trying to minimize the difference between a vector in the range of A and some other vector B. We're trying to find the closest vector in range A to B. Okay, i.e. we want the orthogonal projection of B onto the columns of A. Okay, makes sense? So the closest vector to a subspace spanned by the columns of A is given by the orthogonal projection of B onto the range of A. Now this is a problem that we've actually solved already a couple of lectures ago. So when we were doing projections, we worked out that the projector should be is given by this expression here. Now when we did it in our projection lecture, we did it with complex matrices, so the only difference between what we did there and what we're doing here is we know we're working with real ones, so I'm just writing transposes instead of stars. Okay, so what does that mean? That means P times B will give me the vector I want. Okay, so or A transpose A inverse A transpose B equals AX. Okay, and the other thing we showed that X is given by well, effectively you can just take these A's off. Now it doesn't follow directly from that equation, but we did show this in the other lecture. X is given by X equals A transpose A inverse A transpose B. Or we can write this slightly differently as A transpose AX equals A transpose B. Okay, so that gives us our problem that we have to solve, and that's actually all we have to do. So these are called the normal equations. And in a matter of seconds, we suddenly have the solution to a problem. So if I go back to MATLAB, I can solve my I can find my x by basically solving these equations. So, the normal equations, we want to find x, and I'll call them normal, is equal to A transpose times A. Inverse. Now in MATLAB, whenever we're solving a system, we use the backslash command. Okay, so that means A transpose A inverse backslash A transpose times B means A transpose A inverse times A transpose B. So if I were to run that, that would give me an x. Okay, so why don't we see how good our solution is? So A times x, we're hoping, would be equal to B. So we'll look at A times x minus B. A times x normal. Okay, and we can see that the difference between our points and our model, the residual, is smallish. It's not very small, but it's smallish. Maybe this might be even easier to see if we were to draw a picture. So we'll set up some t's. So t, now I'm going to space out between 0 and 10, and I'm going to plot the model that we've solved. So y, normal, is equal to, if you remember the formula we had, was equal to x of 1 plus x of 2 times sine t plus x of 3 times cosine t. Okay, I'll just break that up so we can stick on the same space. And I'm going to bring back my plot, put hold on so it doesn't delete my first one, and I'll plot t, y normal, in red. See how well it fits my data. Okay, so that's actually not too bad. Let's just make the line width a little bit thicker. So you can see that my least squares solution, here are my data points, the blue circles. This is the best solution to my problem, in that it minimises the sum of the squares of the distances between these points, straight up and down distances, and the curve. Okay, so we're assuming that the errors are only in the y direction. Okay, so the measurement errors are only in y, basically. So the distance we're minimizing is the vertical distance between the line and the points. Okay, that was pretty good. It is possible to do it with the perpendicular direction as well, but that's a much more tricky problem which we're not going to cover in this course. Okay, so great, we've found our solution by the normal equations and we're done. Okay, so often the normal equations will be perfectly adequate to solve. Okay? However, in some circumstances, they can really cause problems, and I'll briefly explain why in a sort of hand-wavy kind of way. So the standard method to solve these normal equations is by something called Cholesky factorization. We will do it later on in the course, so I'll just put the word out now so it doesn't look completely unfamiliar, and when you come back and study, then you'll see the connection. Okay, so that's the standard method to solve these. However, they have the normal equations is the fastest method. Okay, it requires the least computation to find the solution. However, it has drawbacks. Which sometimes can be very serious. Okay, so let's just write the equations down again. I know we haven't defined the condition number of a non-square matrix, but you can imagine we can define a condition number of a non-square matrix in the same kind of way as we did for square ones. So when we're solving this equation, we've basically got A appearing twice when we're multiplying x. So the condition number of this problem is the square of the condition number of A. Okay, so that's a real problem. Because we're multiplying x by A effectively twice, the condition number of the problem is kappa of A squared. Okay, so if you can imagine if it was moderately badly conditioned to start with, let's say the condition number was, say, 10,000, suddenly if we square that, then we have a really big condition number, 100 million, and that means we're losing kind of 8 digits of accuracy when we solve the problem. So if A has a condition number of, say, 10,000, for example, then the normal equations have condition number about 10,000 squared equals 100 million. Okay, so this would mean we'd lose about 8 digits of accuracy solving our problem. And that would not be good. Okay, so when our matrix A is relatively well conditioned, then the normal equations work well and they work fast. But as soon as the matrix A becomes poorly conditioned, then the normal equations becomes a very bad way of finding the least squares solution. Okay, and these matrices A often are fairly ill-conditioned. They end up with a lot of rows which are quite similar, and the condition number can be quite high. So like I said, I'm not really giving you a proper explanation here. It's something that if you're interested in, you could go and do a bit of research on yourself. But just let it be said that this is the reason why the normal equations is not always the standard method, and it's not the method that MATLAB will use if you use its built-in least squares solver. Okay, so let's move on to the more standard way of solving them, or the more accurate way. So method 2, as you may have guessed, is solution by QR factorization. Okay, so if we compute the full, so we did solving the same problem, compute the full QR factorization. So we have A equals QR, where Q is square and orthogonal. Then the residual R is given by AX minus B, like before, just substituting in QRX minus B. And then what I'm going to do is I'm going to multiply both sides by Q transpose, which means I'll get Q transpose R equals Rx minus Q transpose B. Why do I do that? Well, we'll see why in a moment. But basically, one thing we need to note here is that because Q is orthogonal, the norm of Q transpose R, 2 norm, is equal to the norm of R. Okay, it's something we proved when we were looking at orthogonal matrices earlier. Okay, so we can minimize this thing, we can minimize the norm of Q transpose R, and that's equivalent to minimizing the residual. So we can solve this problem and it's equivalent to the original one. So we can minimize R bar equals Q transpose R instead. Okay, and we'll, as its equivalent. To minimizing. Norm R. Okay, so let's write this equation out in a bit more detail. So we've got Q transpose R equals R bar, which equals Rx minus Q transpose B. Now I'm going to write this in terms of the reduced QR factors. So that equals R hat, which is n by n and triangular, with some zeros underneath it, x, minus Q hat transpose and Qn transpose, as we defined in our QR factors lecture, B. And then if we split R bar into the two corresponding pieces, we'll call it R hat and Rn, then we can write this in two sets of equations. Okay, and what are these equations? Well, the first one is that, so looking at the top row, so I can put that back in here if you like, if you don't mind me adding things backwards. Looking at the top set, we get R hat equals capital R hat x minus Q hat transpose B, and we get Rn equals negative Qn transpose times B. So I'm just writing out this matrix expression up here in two pieces. Now remember, what we're trying to do is we're trying to choose x to minimize r. So the thing we're trying to choose is x, and the thing we're trying to make small is r. Okay? Now we know that the norm of the residual, which is what we're trying to minimize, is equal to the norm of R bar, as I just said before, which is equal to, in turn, the norm of R hat squared plus the norm of Rn squared. So we'll consider each piece separately. Okay, so looking at the R hat piece, just going to scroll down a bit now. So I'm going to call these equations 1 and 2. So looking at 1 first, we can make R hat equals 0. Okay, because we can solve capital R hat x equals Q hat transpose B. Okay, and I'm assuming throughout this lecture that our matrix A is full rank, so this system here can be solved. And we can solve that. This is upper triangular, solving for x obviously. This is upper triangular, and can be solved efficiently by back substitution. Okay, so that's great. So we just form the vector Q hat transpose B, and then solve R hat x equals Q hat transpose B by back substitution. Okay, so we can minimize this piece quite easily. Equation 1 is very easy to minimize because we can make it 0. Equation 2, we can't do anything about it. Okay, we can't do anything to change what that value is by varying x. We can't change Rn by varying x, so it is fixed. So therefore, what we've done is we've actually solved the problem. Okay, we've remember the problem was to minimize these two pieces separately by changing x. One of them doesn't depend on x, so all we had to minimize was the first one, and we can make the first piece 0. So basically we've solved the problem. So we've solved the problem. Woohoo! So our least squares solution is x equals r hat inverse q hat transpose b, which we can solve by back substitution like I just said, and the residual finally is norm r equals the norm of r hat, plus the norm of Rn, just equals the norm of q hat transpose b. Okay, so that's really neat. So that is the way that we solve this, that we solve the least squares problem by the QR factorization. So remember, we've done the same thing, except we haven't had to form this these normal equations which involve multiplying the matrix A together, and so this is a much better way. So let's go to MATLAB and do that too to finish off with. So heading across to MATLAB. So we want to solve this now by the QR factorization. So let's just turn this into a slightly more comprehensive file. This one is loading the data. Okay, I'll tell you why I'm doing what I just did then in a moment. Okay, so I'll start my file off by clearing everything out, and I will load up my data again. So there we go. So the same set of data as I had before, and I'm going to now try and solve this problem by QR factorization. So I've defined my A, I've defined my B. I don't want to use my normal equation solution. I now want to do solution by QR factorization. Okay, this is simplicity in itself. If we just look back to what our solution was, our solution is given by x equals r hat inverse q hat transpose b. So x least squares, so xqr we'll call it, is equal to, well, we can't do it yet because we don't have the QR factorization. So what I'm going to get is my reduced QR factorization of A. Okay, so let's just hide that for now. Let's check it works. So I've done the reduced QR factors, so QH should be the same shape as A. It is. And R hat, which I've called RH, should be upper triangular, which it is. So that's great. Now our solution is just given by R hat inverse, so R hat backslash in MATLAB, times Q hat transpose B. Is that right? Yep, Q hat transpose B. Okay, so XQR looks very much like the X I got for the normal equations before. Let's just do that one again. Don't really want a picture of those. So X normal and XQR, they look pretty similar to me. Actually, how similar are they? Let's have a look. XQR minus X normal. Okay, because I've actually got a really simple, well-conditioned problem, they're only different at a very high number of decimal places. Okay, so that's good. Okay, so we've solved our problem, so we can do the same thing as we did before, and we'll define a y so we can plot our results. Now, as you can see, because these things are virtually the same, it'll just look the same as it did before. So I'll grab that, change this into QR. and again. Okay, and I'll take that same set of t values, which in fact, nope, don't want that. What have I done? Done something silly. Let's dock you back in there. Okay, I'm just going to stick that t command up in here. Okay, so what we should be able to do then is plot t yqr, and I'll plot this one in green, or yeah, green with a line width of 2 as well. Okay, so what we should now see is there's a solution. We've lost our data points though, so we'll get those back. There they go, and we'll add on to that our QR factorization solution. Okay, and there it goes. So we've got the same answer as before, it all worked, and our least squares solution is that sinusoid, and it's exactly the same as the normal equations one for this problem. Okay, so that's pretty much where I want to get to. There's one more thing I want to mention before we finish, but we're almost there. So we've solved our problem by two methods. Let me just make a note about the conditioning of this one. This problem, I'm not going to say why because it's complicated, but this problem is better conditioned than the normal equations. And is the standard method. Okay, actually going into what the conditioning is a bit beyond the scope of what we've got time to do in this course, and it's the standard method. Okay, and oh, I should mention one more thing. In MATLAB, you don't actually have to do it this way. MATLAB has its own built-in routine for least squares, and funnily enough, it's actually backslash. So if I just take A backslash B, and I've got a matrix A and B, which are the shape they are. So remember, A was, I don't know, 11 by 3, and B was 11 by 1. If I take A backslash B, so I'll just call this X backslash, that actually knows that, well, it does the least squares solution. If it's got an overdetermined system, backslash automatically computes the least squares solution. So that's a trap to be aware of, because sometimes you might be expecting it to just try and solve a linear system. It automatically does the least squares one if your system is overdetermined without warning. Okay, so just something to be aware of. But it's also a very helpful feature as well, because often that's what you want. So we don't actually have to do what I've done up here. We can let MATLAB do it for us by using backslash. When MATLAB does this, it uses the QR factorization method to solve this problem. Okay, so one last thing to say. We can modify our problem slightly. So I'm still looking at an overdetermined system. We'll do underdetermined next lecture. Weighted least squares. Just going to give it the briefest of mentions. There'll be a problem on this in the tutorial. So maybe some problems, or some data points, sorry, are more important than others. Okay, so what we do is we multiply, we don't have to, multiply each element of the residual by a weighting. Okay, and I'll call it WII. Okay, so for example, if we had M was equal to 4, we had 4 rows in our matrix, and we really wanted to make sure that the fourth equation was minimized more kind of vigorously than the rest of them, then we might set the weighting for number 4 to be 10, and the weighting for the rest of them to be 1. Okay, so what we do is we stick these into a diagonal matrix, So we might do something like this. Gives more weight or expends more effort in minimizing the last component of the residual. Okay, so how do we do this? Well, we set it up in a matrix, so W is equal to a diagonal matrix of the WII's. Okay, that's how I write a diagonal matrix in compact notation. Okay, and then the problem just becomes minimizing W times AX minus B squared. Okay, so in other words, A gets mapped to WA, A becomes WA, and we replace B with WB, and we're in business. Okay, so just to finish off, we'll do that for our problem we had on the board before. So if let's say we'll just plot our solution up again. If is it gone? It's gone. So we'll just get our solution back, and we'll plot our least squares solution. Okay, let's say that. Let's see, what point is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say that it's really important that our curve goes straight through point 9, or that we try and get it closer to point 9. It's more important that it goes near point 9 than the other ones. What we do is we want to weight point 9, or the ninth point, by some number. So if I'm going to define a weighting matrix, which is going to be the identity. Okay, and I will need, just check what size it is, 11 by 11. That's good. And I'm going to make the ninth diagonal element, say 100. Okay, and now I'm going to solve W times A backslash W times B. That's just in the least squares solution. Doesn't look quite the same as before. So if you look at the one we had before, it now looks a bit different. So I'll plot my solution. I'll just type it in directly. So it'd be X, what did I call it? X BS plus X BS of 2 times sine t plus X BS of 3 times cosine t, and I'll make that one red and dashed. Okay, so if we now look at what we've got, and I'll make it thicker too. If we look at our picture, because we put that higher weighting or the higher importance on our curve going through this point, the whole thing's been shifted so that it actually goes, probably doesn't go exactly through it, but it's trying a lot harder to go near this point than it is to go near the other ones. Okay, so it's very easy to import and to introduce some kind of weighting into our least squares problem. Okay, well that's about enough for this lecture. So next lecture we're going to look at underdetermined systems and some other applications of QR, and then we'll be done with this topic. So until next time.